Hi, this is an example problem from Chapter 19 about energy storage in an automatic electric defibrillator. Pause for a moment and read the question. So we've got an automatic electric defibrillator here, which uses a capacitor to store electrical energy, electric potential energy, which can then be released as the charges flow as a current through a person to get the heart started again. Let's look at part A. What is the voltage that exists across the capacitor plates when it is fully charged? So just a few important equations about capacitors. The charge on the stored by the capacitor is equal to the capacitance times the voltage of that capacitor, or the voltage across that capacitor. Again, we usually think of this as the delta V, but we're going to just, for simplicity, write this as V in this case. The capacitance for a given voltage, how much charge can you store? All right, now, but we're starting in part A with energy. So we know we've got capacitance C is equal to 120 microfarads. And the amount of energy stored, I'm going to write this as the electric potential energy. It's equal to 73 joules. How do we figure out V? Not from the equation I just wrote. We're going to need to look at a different set of equations to figure out how the voltage, the capacitance, is related to the amount of energy you can store in a capacitor. Turns out that there's an equation here, or several equations here, but in this case we know what the energy is, and we know what the capacitance is. We're looking for the voltage. We're going to use this one right here. 1/2 CV squared equals the stored energy. And we're trying to figure out V, so we got to do a little bit of algebra here. Well, let's do it like this. Go ahead and multiply by 2 over C on both sides, and cancel out some C's, 2's. And if we turn this around, we are going to end up here with V squared is equal to 2 times the stored energy divided by the capacitance, and then we're going to just go ahead and use our square root there. Now to get the answer for V, let's plug in our values. Now I converted to farads, the SI unit for capacitance, because I want to be sure with all these new units that I'm in SI units, so when I do a calculation I'll come out with the correct answer in SI units. Plugging this into the calculator, we get an answer of about 1100 volts. Alright, let's look at part B. What magnitude of charge resides on the capacitor plates? Here we can use the equation I showed you earlier that relates charge, voltage, and capacitance. So Q is equal to the capacitance times the voltage across the capacitor. That's going to be 120 microfarads multiplied by 11,000 volts. And that comes out to about 0.13 coulombs. Now, how do we know that farad times a volt a coulomb? Well, we remember that we're in SI units, and so we're going to come out with the right thing here. Now, the voltage in the defibrillator here is huge, 1100 volts, whereas the battery that generates that voltage usually, has maybe like 9 volts or something like that. How does that work? I had to look this one up myself, but what I found out is that ordinarily to get a voltage like this would require a very large battery stack, hundreds of individual like 9-volt batteries or something, right, to get that voltage. Instead, a defibrillator, it uses a small battery pack to drive what we call a chopper circuit that steps the voltage up through a transformer, after which the result is rectified filtered and stored in a low leakage capacitor bank, which minimizes the weight and bulk of the machine as well as its cost. So there's definitely a lot going into that. We'll learn a little bit more about some of those ideas in the future in this course.